And let me start by giving some motivation to explain why we need that kind of thing. So imagine we have Alice and Bob, and they're talking to each other, they're executing some type of protocol over the internet. So they're sending messages back and forth. Okay? And at some point, Bob starts becoming a little suspicious. Did Alice actually follow the protocol, or is she trying to pull some kind of trick on him? So, well, he asked her to reveal her inputs so he can check for himself that she followed the protocol. And now it's Alice's turn to get a little suspicious. Why is it that Bob wants to know all her inputs to the protocol? And she says, no. Okay? So we have this clash. On one hand, Bob, he wants some kind of verifiability, right? He wants to verify something. And on the other hand, Alice, she has something that she wants to keep private, and she doesn't want Bob to see. Okay? So the problem is, I mean, she's willing to give this one bit of information that she did follow honestly the protocol. It's not like she wants to put herself in a bad light, but she doesn't want to reveal anything else beyond that. Okay? So there's this kind of very fundamental clash between privacy on one hand and verifiability on the other hand. And zero-knowledge proofs can help us overcome this difference between privacy and verifiability. Okay? So a little bit of the history of the zero-knowledge proof. There was something that was introduced in 85. Actually, a bit before that, I think it was 83 or something like that, they started submitting, but you know, people kept rejecting this crappy paper until they decided instead to accept it and give it the Gödel Award. Okay. So what is a zero-knowledge proof? Well, let me explain what an interactive proof is. Okay, so it's kind of a generalization of a mathematical proof that you're all familiar with, right? You have a theorem and statement, and then you give a long proof, and you convince everybody else that it's true. And what they observed was that you could do this in an interactive fashion. Okay, so you send some messages, get some challenges, send some more messages, and in the end you convince the verifier that the statement is true. Okay, so now we have this interactive protocol between what we will call the prover and the verifier, and in the end the verifier is happy, says, okay, now I'm convinced the statement is true. And it can be all kinds of statements, right? So it could be mathematical theorems, it could be some kind of identification protocol where Alice wants to convince Bob that she is indeed Alice. Could be some kind of verification where Bob wants to check that Alice followed the protocol. And full generality, what we'll be looking at are statements that X belongs to a language L, which is an NP language. Okay, and then we can reduce all kinds of efficiently verifiable statements to this NP language, and hence give interactive proofs that it belongs to the language. Okay. So the statement is the form, X belongs to this language, and the prover knows that it belongs to the language. The prover has a witness that it belongs to the language. And now they can engage in this protocol, and the prover will convince the verifier that X belongs to the language. Okay, so now this is, of course, something that's trivial to achieve if we don't care about privacy, because then the prover could just send the witness, right? And then the verifier could check that indeed X belongs to the language. But we want to have some level of privacy as well. And I'm going to talk about two types of privacy. One is zero knowledge, and the other one is witness indistinguishability. And zero knowledge roughly is that the verifier learns that the statement is true, so we do reveal a little bit, one bit of information, but we don't reveal anything else. Okay, so everything else is kept private and is not learned by the verifier. So this is kind of a very strong notion of privacy, and I'm going to use a weaker one as well, which is called witness indistinguishability. And there we're looking at statements. So if we look at one particular statement, it may have many different witnesses for belonging to the language. Okay? And a witness indistinguishable proof is one in which the verifier does not learn which of those witnesses it is that the prover has in mind. Okay? So it doesn't exclude, so certainly zero knowledge implies in particular that the verifier does not learn which witness it is, so zero knowledge clearly implies witness indistinguishability. It doesn't go the other way, right? It could be, for instance, that all witnesses have the first bit is 0, and in that case there's nothing wrong with giving a proof that reveals that the first bit is 0, because it would not help the verifier to distinguish between the witnesses. Okay, so let me continue this history a little. Okay, so we have now interactive zero knowledge proofs. The problem is that there are a lot of things that are non-interactive in nature, right? If you sign a message or you encrypt the message, it's something you do locally on your computer, and then you put it in an email and you send it off, right? There's no interaction between a prover and a verifier. And we would like to have zero knowledge proofs that can be used in connection with these kind of tools. So we would like to have non-interactive zero knowledge proofs. Okay? So one could imagine that a non-interactive proof looks something like this. Okay, so we still have the statement, prover knows the witness, and now the prover just sends one message that convinces the verifier. Okay, and to clarify a little what are the properties that we want. Okay, so on one hand we want completeness, that if indeed X belongs to the language, then it should be possible for the prover to convince the verifier. We would also like to have soundness, that it's not possible to convince the verifier if the statement is false. So no matter what a cheating prover does, she would not be able to convince the verifier if the statement is false. And then we would like to have zero knowledge, that the prover reveals nothing except that the statement is true. And the standard way of defining zero knowledge is that you say basically that it's possible to simulate the proof. Okay, so it would be possible for the verifier to simulate the proof, and hence, since the verifier can simulate the proof, it cannot actually learn anything from the proof. Now there's a problem, which is that non-interactive zero knowledge proofs, they don't exist. Okay, but they only exist for trivial languages. Okay, and I'll just quickly sketch why that is so. Okay, so imagine we have some language which has a non-interactive zero knowledge proof. Okay, and we'll construct a decision algorithm for X. Okay, and what it does is simply it simulates the proof. Can do that because it's zero knowledge, and then it runs the verifier protocol on this simulated proof. And there are two cases, of course, right? One is if X does belong to the language. Well, by the zero knowledge property, we can simulate the proof, and by the completeness property, that should be accepting. And if X is not in the language, then the soundness property says that the verifier should reject. Okay? So if we have a language which has a non-interactive zero knowledge proof, then it's actually very easy to decide whether X belongs in the language or not. So that's only possible for trivial languages. So we're kind of stuck in this situation, right? We have interactive zero knowledge proof. We have a lot of non-interactive things that we would like to use, and we would like to be able to give non-interactive zero knowledge proofs, but they're impossible. Now, the fact that something is impossible is not something that's ever stopped cryptographers. So what Bloom, Feldman, and Cowley was, they introduced non-interactive zero-knowledge proofs in the common reference string model. Okay? So we're not in the plain model anymore. We are going to assume that there's some type of setup. Okay? The common reference string model basically says that there's a bit string that's available to both the prover and the verifier. Okay? And we're assuming that this common reference string has been generated honestly. Okay? It could be either a uniform random distribution of bits, or it could be that it's some kind of specific distribution. And the example I'm going to give later assumes very specific type of common reference string. And I'm not going to talk much about how this common reference string comes about. Okay? I mean, it could be that they just blindly trust some trusted party. It could be that they use some kind of secure multi-party computation protocol. It could be that, well, there are various other models, for instance, the multi-string model, where you assume not that there's one string that's honest, but there's n strings, and you assume that t out of those n strings are honest. Okay? So, but for the purpose of this talk, I'll just assume that we have a common reference string that has been generated honestly. Okay. So now the picture looks like this. We have a common reference string, and we have a statement. And we would like the prover to just give a one-message proof that convinces the verifier that the statement is true. And we would like it to be zero knowledge, that the verifier doesn't learn anything but the truth of the statement, or, which is also useful, just that it's witness indistinguishable, that the verifier does not learn which out of many possible witnesses the prover had in mind. And I'm going to go through now defining what more precisely what non-interactive zero-knowledge proofs are. Okay? So they consist of three probabilistic polynomial time algorithms. One K, which generates a common reference string. And then we have the algorithm run by the prover, which takes as input the common reference string, the statement, and the witness, and outputs a proof. And then we have the verifier's algorithm, which takes as input the common reference string, the statement, and the proof, and either accepts or rejects the proof. Usually the verifier is actually a deterministic algorithm. And we have these properties we would like to be complete. We would like to be able to convince verify if indeed the language X does belong to the language. We would like it to be sound, such that we can't cheat on the false statement. And then we would like to have some privacy properties, either witness indistinguishability or zero knowledge. So completeness is defined in the following way. We look at this experiment. So first we generate a common reference string, and then we let the adversary generate a statement and a witness. The prover runs the algorithm for generating the proof, and the verifier decides whether to accept or reject. And we would like to have completeness, which means that in this kind of experiment, the verifier will always accept. Okay? And note here, the reason we let the adversary generate the statement and the witness is because now we have actually the worst case scenario. Even on the worst possible statement, the worst possible witness, will still be able to convince the verifier. Okay, so the second property we want is soundness. So again, we generate a common reference string. And this time the adversary comes up with a statement that's false. And the adversary also tries to come up simultaneously with a proof that will convince the verifier. So again, the verifier accepts or rejects. And we say that the non-interactive zero-knowledge proof is sound if the probability of rejection is very large. Okay, and now I'm going to distinguish here between perfect soundness which means that if the statement is false, the verifier will reject no matter what. And computational soundness, where we're just saying that a polynomial time bounded adversary has low chance of convincing the verifier on a false statement. Okay. I want to point out one distinction here in soundness. So soundness can be defined in a non-adaptive fashion or an adaptive fashion. Then the non-adaptive fashion is where the statement is chosen independently of the common reference string. And the adaptive soundness is when actually the adversary sees the common reference string first, and then after that it generates the statement and the proof. Okay, and obviously adaptive soundness is a stronger notion, and I think it's a much more realistic notion because, well, the common reference string is public. It's not assumed to be private. It's out there. So it's very reasonable to assume that this is something that the adversary might get hold of. And the reason I'm pointing out this because sometimes you see papers talking about non-adaptive soundness, and I really think that the right notion is an adaptive form of soundness. Okay, so soundness protects the verifier, right? It means that you can't fool the verifier into accepting a false statement. Now we're going to try to protect the prover. So witness indistinguishability we define with the following experiment. So first we generate a common reference string. And now the adversary comes up with some statement and two different witnesses. Okay? And the prover flips a coin and uses one of them to generate a proof. And the adversary tries to guess which of those witnesses has been used. Okay? So it's very similar to, for instance, the way that you define indistinguishability on the chosen plain text attack of encryption. Right? The adversary is trying to guess which of the witnesses has been used. And we say it's witness indistinguishable if the adversary has small chance of guessing which witness has been used. Okay? So that, again, I'm going to distinguish between perfect witness indistinguishability, where the adversary has just 50% chance of guessing which witness has been used, and computational witness indistinguishability, which just says that a polynomial time adversary has roughly half probability of guessing which witness was used. Okay, moving on to the stronger notion of privacy. We have zero knowledge. Okay, and I'm going to compare two different experiments here. One where we actually run the real proof. Okay, so we generate a common reference string. Adversary chooses a statement. The prover gives a proof. And I'm going to compare that to a simulation. Okay, so in the simulation we simulate a common reference string. Adversary comes up with some statement, and now we simulate a proof. And we're going to say that, well, in both cases, the adversary comes up with a guess. It tries to guess whether it's looking at a real proof or whether it's looking at a simulated proof. And we say we have perfect zero knowledge if the odds of guessing one is exactly identical in those two experiments. And we say it's computational zero knowledge if a polynomial time adversary only has negligible advantage in guessing which of those games it is. Okay? And the reason we say this is zero knowledge, it doesn't reveal anything, is because the simulator obviously doesn't use the witness at all, right? So it can't leak any information about the witness to the prover. And the reason we need to have some kind of setup is because we do need to give the simulator some kind of thing that will enable it to simulate. And what it gets is actually a trapdoor tile associated with a simulated common reference string. Okay, This is the definition of non-interactive proofs with either witness indistinguishability or zero knowledge. And if you have any questions about the definitions or anything I need to clarify, I guess this would be a good time for questions about that.
So witnesses are known to the verifier, or is kept secret?
So the witness, so the witness is known to the prover because the prover needs it to create the proof. Okay, we're not making any assumptions of what the verifier knows. Okay, it might know the witness, it might not know the witness. We can't tell. Okay.
You can say which witness is used, like the prover, the verifier does not know that. It means that he knows it. Right?
So if you're thinking about this definition of it, right, where we let the adversary generate the witnesses, and that's basically because we want to capture as strong a notion of witness indistinguishability as we possibly can. And the strongest notion is that the adversary knows everything, right? So it actually knows it could be either this witness or it could be that other witness. Okay? But that kind of incorporates also the weaker situation where maybe the adversary didn't know which of those witnesses it is. Okay. Any other questions about the definitions? Yeah.
Latter model, the computational version.
In here?
Yeah, it seems odd that this computational adversary is able to generate that every pair in the first place. This is an empty predicate, right?
So you're saying it's kind of odd that it is possible to simulate, or?
Our polynomial find adversary probably wasn't able to generate an XW pair, right?
Oh, I think it's pretty straightforward to generate a statement and a witness for an NP language, right? Consider, for instance, a circuit, right? I mean, you can just say, okay, look, I want to create a circuit, and with this input, it should output 1, and that's pretty straightforward to generate.
But we're quantifying over all X explicitly, right?
So the way the quantification works, so you could define, again, there's this question of whether it's adaptive or non-adaptive. So typically a non-adaptive definition would be just that you kind of quantify over all X. It should be, in all X in the language, it should be such that you can't distinguish. So what you would do, you would simply take X and W. You still have to give something to the prover. So you would just quantify over all X and W. Okay. In the adaptive version, we give the common reference string first to the adversary, and then the adversary might actually pick a statement and a witness that depends on the common reference string, right? So this is kind of a stronger definition. But then, so it kind of, the quantification then is that this kind of goes into the probability statement and the experiments. Hope that answers your question. Okay. Okay. So I want to mention that there's one trade-off here, and that is that we can't have perfect soundness and perfect zero knowledge at the same time. We do have to make a choice. And again, quickly to sketch the proof is, suppose we had a language which had a common reference string non-interactive zero knowledge proof, which had both perfect soundness, perfect zero knowledge, then you could actually decide whether X belongs to the language or not. Okay, the way you would do it is you would run the simulator to generate a common reference string. You would simulate the proof, and you would run the verifier on the simulated proof. Now, if X is in the language, then by the perfect zero knowledge and the completeness, the verifier will accept. On the other hand, if X is not in the language, then by the perfect soundness, the verifier would reject. Okay? So it's actually very easy to decide a language which has both perfect soundness, perfect zero knowledge. So if we're looking at general NP languages, we have to make a choice. We could either get perfect soundness and computational zero knowledge, or we can get computational soundness and perfect zero knowledge. Or they can both be computational, of course. You can, in general, you can transform these proofs into proofs that have perfect completeness. So there's kind of no loss of generality, assuming that the verifier algorithm is deterministic, which it usually is in these kind of schemes. So the reason is basically what the prover would do is it would give a proof, then it would run the verification algorithm itself to check that the proof was actually valid. And if it's not valid, which happens with negligible probability, but if it's not valid, it would simply send the witness in the clear. Okay? Now you have perfect completeness, and since there's very negligible probability of actually ending up with an invalid proof, then there's no loss of generality in assuming you have perfect completeness. And it does make things easier to reason about when you have perfect completeness.
The first implication is skeptical.
Uh-huh.
In both predictive and non-predictive cases.
That's a good question. I think it does. Yes, it does, because if you're thinking about perfect soundness and perfect zero knowledge, then the two cases are actually identical. Okay, because perfect means that there's no chance whatsoever of distinguishing, and then it's kind of the same. I mean, if whether you had it before or after the common reference string, it doesn't matter, because they just don't exist in the cases where something bad happens and the property is broken. Okay. There are tons of applications of non-interactive zero-knowledge proofs. Okay, so it was used in some of the first constructions of chosen ciphertext attack secure encryption. Now we have other techniques to do that, so I don't think it's the prime example of using non-interactive zero-knowledge proofs. You can use it in voting protocols. It's been used a lot in various types of signature schemes, right, where you want to have some level of anonymity, and at the same time you want to verify something about the signature. And I'm going to give you an example of a ring signature later on. And there are lots of other applications of non-interactive zero-knowledge proofs. And for that reason, there's been quite a lot of research in non-interactive zero-knowledge proof. And this is kind of like a snapshot of the world in 2005. Okay? So there had been a lot of research in non-interactive zero-knowledge proofs, starting from the definition, and then efficiency improvements, constructions that were based on general assumptions such as trapdoor permutations, and efficiency improvement, again, by Killian and Petrank, attempts to shorten down the size of the common reference string. But despite all this research, all the schemes were really inefficient. And since there are a lot of cool applications of non-interactive zero-knowledge proof, people tried to come up with various other shortcuts. So one would be to use the Fiat-Shamir heuristic, where you take an interactive public coin proof and you use a cryptographic hash function to compute the challenges from the verifier, this way making it non-interactive. And you can prove in the random oracle model, if you model a cryptographic hash function as a completely random function, that this is secure. But there are also various examples that actually show that the random oracle model is wrong, that it leads to insecure instantiations. And I think it's still a big open question. Okay, does this method actually produce valid non-interactive zero-knowledge proofs or not? I mean, for natural protocols, we don't know of ways to break this way of constructing them. On the other hand, we don't have any way to reduce the security to some kind of standard cryptographic interactability assumption. Another alternative would be to use designated verifier proofs, so proofs that can only be verified by a specific verifier instead of being verified in public. So the proofs I just described in the definition, I just described the soundness, actually anybody can come and verify, because it just requires the common reference string, the statement, and the proof, okay, which could all be public information. So it's actually publicly verifiable. And I think this is a key point in non-interactive zero-knowledge proofs when you compare them with interactive proofs, is that a non-interactive zero-knowledge proof, that's something you can copy and you can give to somebody else, and they can verify as well. Okay? So it's a transferable type of proof. As soon as you have just one more round, you have some interaction, then it's not something you can easily copy, because somebody gives you a transcript of an interactive proof. It might be that they had picked some particular challenges from the verifier and matching messages from the prover. So one big benefit of having non-interactive zero-knowledge proofs is that they can be copied, they can be transferred. Okay, so what we are going to show here is that pairing-based techniques can actually be used to construct efficient non-interactive zero-knowledge proofs. And we can reduce it to standard-style cryptographic assumption, and we don't have to use these kind of heuristic ways of generating non-interactive zero-knowledge proofs. Okay, so the contributions I'm going to talk about is one is the practical aspect. Okay, so what we had was the most efficient proof was by Kilian and Bertrand from '98, and it was a proof for circuit satisfiability, and it was fairly inefficient, not the kind of thing that you would use in practice. And then when we started introducing pairing-based techniques, what we came up with was an efficient proof for circuit satisfiability. Somehow that's actually not really what we want, because if you look at some kind of practical cryptographic statement, then it's actually very costly if you have to first go through an NP reduction and produce a circuit, and then you prove the circuit. Okay? What we really want is non-interactive zero-knowledge proofs for practical statements. Okay? I came up with one construction which was inefficient, but did prove practical statements. And the problem with construction is that the constants are absolutely enormous. And later on, we came up with a way to actually give efficient non-interactive zero-knowledge proof for the things that you want to do when you design cryptographic protocols, and without having to go through a reduction to circuit satisfiability or some other general NP complete language. So that's kind of the practical contribution, and I want to kind of make specific what I mean by inefficient and efficient. Okay, so consider a statement, something that would typically happen in the design of cryptographic protocols. We have a ciphertext. It encrypts the signature on this document. Okay, and if you use Kilian and Bertrand's proof, we're talking about something like a gigabyte. So not the kind of thing that you would attach to an email and send out. And now like a kilobyte. So there's really a significant gain here by using pairing-based techniques. I also want to talk about what pairing-based techniques can tell us about the theory of non-interactive zero-knowledge proofs. And again, I kind of want to draw a little upon the history. So we had interactive proofs. They were introduced by Goldwasser, Michali, and Rakov, and Goldwasser, Michali, and Victorson pretty fast showed that you could actually use that for all of NP and for NP complete languages and get computational zero knowledge. And Rosard and Croppo, show that you can also get perfect zero knowledge in the interactive case. And Bloom, Feldman, and Macaulay, when they introduced non-interactive proofs, they showed that you could get computational zero knowledge. Now the last field here, that was actually an open problem for quite a while. And it turns out with pairing-based techniques, you can actually get non-interactive zero knowledge proofs that have perfect zero knowledge. Okay? And I think perfect zero knowledge is important because, well, we'll live in a world where we don't quite know whether, say, quantum computers come about sometime in the future, or some of our cryptographic assumptions are broken in the future. And in that case, it's actually nice to have perfect zero knowledge, that the proofs don't contain any information whatsoever, because otherwise you could imagine the adversary stores the information today, right? And then 10 years later, when there's a significant mathematical breakthrough and you can break discrete logarithms and things like that, it could take back what it had archived, right, and say, oh, this was the information that you used. Now, if it's perfect zero knowledge, can't do that. There's no information in the zero knowledge proofs. So on the other hand, I think typically when you use these kind of protocols, soundness is something you need right away. So that's more reasonable to make some kind of cryptographic assumption, right? If I'm running some kind of, using a non-interactive zero knowledge proof in some kind of voting protocol, then presumably I'm counting the votes now, not 10 years into the future. Okay, so in the rest of the talk, I want to introduce pairing-based techniques in the construction of non-interactive zero knowledge proofs, give you a simple construction of a non-interactive zero knowledge proof. And this is also one of the nice properties of pairing-based techniques, that you can actually give a simple construction. Typically, the previous constructions were quite involved. Then I want to talk about how to get perfect zero knowledge. And then finally, I want to talk about how to get efficient non-interactive witnessed indistinguishable proofs. And I'm giving a concrete example with applications to ring signatures. Okay, so the first thing I'm going to show you is a non-interactive zero knowledge proof for satisfiability, which has perfect completeness, perfect soundness, and computational zero knowledge. And the common reference string is very short. It just consists of a few group elements. Okay, so this compares quite favorably with previous constructions that really had huge common reference strings, many gigabytes. And the proof size is going to be basically one group element, a constant number of group elements per gate in the circuit. Okay, and I'm going to use pairing-based techniques. So we've already seen that a couple of times through this workshop, right? I'm going to work over cyclic groups that have a composite order. Okay, so I'm assuming these are cyclic groups with order n, where n is an RSA modulus, product of two primes. I'm also going to assume for the purpose of this talk that the two groups that we use the pairing on are the same. So this is kind of a symmetric setting. You can generalize everything here. You can use prime order groups. You can use different groups here. But it complicates things, and I'll just try to keep it as simple as possible. I'm also going to make an assumption, and the cryptographic assumption I'll use is the subgroup decision assumption, which says that if we have an element H, it's hard to distinguish whether H has order Q. In other words, it lives in some kind of subgroup, or it has order N and generates the entire group. Okay, so this assumption was introduced by Bonego and Nissim, and they used it to build a crypto system. And it works like this. So we have a public key that consists of a generator for the group, and then H, which lives in a subgroup, has order Q. And the secret key is the factorization of this order N. To encrypt the message, we compute a ciphertext, which is G raised to the message A. and then h raised to some randomness. And to decrypt, what we do is we compute the ciphertext raised to q, and since h has order q, it gets killed by this q, and what we're left with is g to the q raised to the message. And if the message is small, if it's just a few bits up to a logarithmic number of bits, then we can do a brute force attack and compute the discrete logarithm and get out the message A. And it's chosen plaintext tag secure if we under the subgroup decision assumption. Okay, sketch of the proof is that basically the adversary cannot distinguish whether it's looking at a public key where h has order q, or where it's looking at public key where h has order n. But if h has order n, then you can, if you look at the encryption, then h raised to r, that's just a random group element. So the ciphertext will be a random group element, and it contains no information about the message. Okay, now first let me just change terminology and call this a commitment instead, but it's the same kind of scheme. We commit to a message A by taking G to the A and H to the R. And I'm just after the perfectly binding property that a commitment defines a uniquely modular P. And the reason is that H has order Q, so H can randomize things happening in the order Q subgroup, but it cannot influence what happens in the order P subgroup. And therefore, a commitment uniquely defines a modular P. At this stage, I'm not assuming that we can actually decrypt, because I'm saying it's permissible that A actually is large. And it hides what the message is, again, because we cannot distinguish whether H has order Q or H has order N, and if H had order N, then it would be informationally theoretically hiding the message A. Okay, so this is the fundamental building block in the non-interactive zero knowledge proof, this type of commitment scheme. So why wasn't this a cool thing when they introduced it? Well, it has some really nice homomorphic properties. The first one is that if you take two ciphertexts and you multiply them together, you get a sum of the plaintext. Right? So if you take two commitments, multiply them together, you get a commitment to A plus B, modulo N. At the same time, you also have a multiplication operation. If you take two commitments and use a pairing operation on them, then you can do various computations, and what you end up with is essentially a commitment to A times B. Right? Notice here that here we have a pairing, the second term is a pairing of H with something. H has order Q, and therefore the pairing of H with something has order Q. So everything here just has order Q. What we're left with is this term here that, since G and G is a generator for the target group, is something that may have different order. So we essentially get the same type of commitment to A times B. Now there's one catch here, which is that once we've done the pairing, we're in the target group. So we can't do this again. We can't do infinite multiplication. We only get one multiplication. But it turns out that one multiplication is enough to give us non-interactive zero-knowledge proofs. And I think it's instructive, again, to compare this with previous works. I mean, of course, homomorphic, additively homomorphic commitments, they have been known for a long time. Peterson commitments are additively homomorphic, and it's basically that kind of commitment scheme that we're using. So what really gives us the power to build non-interactive zero-knowledge proofs is that now we both have additions and multiplications. Okay, so that's the building block that we're going to use in the non-interactive zero-knowledge proofs. Any questions about the building block, about these BGN commitments? Okay. Okay, so now I'll give you a construction of a non-interactive zero-knowledge proof. Okay, I'm going to look at a circuit for the purpose of illustration, a very simple circuit, and I'm also, for simplicity, assuming that it just consists of NAND gates. There's only a constant factor loss in assuming that. And obviously, circuit satisfiability is NP complete, so if we can give non-interactive zero-knowledge proofs for circuit satisfiability, we can give non-interactive zero-knowledge proofs for all languages in NP. So what the prover wants to convince the verifier is that, look, here's a statement, here's a circuit, and the claim is that it's satisfiable. So in other words, that there's some way to make this circuit output 1. And the witness that the prover has are the values of the wires that will make the circuit output 1. Okay, so prover's witness consists of values to these wires such that it will output 1. Okay, so now we want to give a non-interactive zero-knowledge proof. And the strategy is as follows. First, the prover commits to these values. Okay? And since the commitments are hiding, it doesn't actually reveal to the verifier what the witness is, right? It just commits to the wires. Okay? And the output wire is going to make a trivial commitment with randomness 0. A trivial commitment to 1, such that the verifier can easily verify that, yes, the output is a commitment to 1. And the strategy now is that we would like to, first of all, we would like to prove that these committed values, these committed wires, do actually belong to 0 or 1, okay? They're either true or false for each wire. In principle, of course, the commitments, they could be anything modulo p. So we kind of want to rule out that they're anything in modulo p. We want to prove that we have committed to bits, either 0 or 1. So that's kind of the first step. And the second step in the proof is that we want to prove that these wires respect the NAND gates. Okay, so let's start with the first one. So now suppose we have a commitment, just one commitment, and we want to prove that it contains 0 or 1. Okay, so I can write the commitment as g to the w, h to the r, and w is actually uniquely defined modulo p, since h has order q. Okay, so the verifier obviously doesn't know what w is, but it knows that there's some uniquely defined w inside the commitment. And if we do some computations, we look at this pairing of the commitment divided by g. So by the additive homomorphic property, that's actually either so the first one is a commitment to w, the other one is a commitment to w minus 1. And if w is 0, then the first one, that's just h to the r, right? So that has order q. If w is 1, then the second one is just h to the r. So in other words, it has order q. So if w is 0 or 1, this element here, this paired value, will have order q. On the other hand, if w is anything else, we'll see that it doesn't have order q. So basically the strategy is look at this pairing and then try to convince the verifier that it has order q. So doing some further computations, we can see that this thing here is actually equal to this value here, w times w minus 1, right? And then we have h with something else. So this one automatically has order q. And if w is 0, 1, then of course this term just cancels out, and there's nothing left. The proof is going to be this term in here. So that's what the prover will send to the verifier. And the verifier will check that when you pair the ciphertext and the commitment and commitment divided by g, then you'll get the pairing of h and the proof. And it's easy to see that it's perfectly complete, right? Because if W is 0, 1, then this term here cancels out. There's nothing left. And indeed, we would have this equality. We also have perfect soundness because, well, we could rewrite this thing here as follows. And now we have this term over here has a pairing of H with something, so that has order Q. This is a pairing of H with something that has order Q. So in this thing here is the only thing that may not have order Q. And indeed, if W is different from 0 and 1, it will be something that is non-trivial in the order P subgroup. Okay? So in other words, if this equality holds, this thing here must be 0, and we can conclude that W is 0 or 1. So it's actually a very simple proof that a commitment contains 0 or 1, right? The proof just contains one group element. And the verification is very simple. You just pair H with pi and do this check here, and then you're convinced that the commitment contains 0 or 1. So that's kind of the first part of the non-interactive zero-knowledge proof. Now we know how to prove that the commitments contain 0 or 1. And the next part is to prove that if we have 3 commitments, and then that one commitment contains the NAND of 2 other commitments. And I'm going to use an observation for that purpose, which is that if we have bits B0, B1, and B2, then B2 is a NAND of B0 and B1, if and only if B0 plus B1 plus 2B2 minus 2 is 0 or 1. Okay? So yeah, you can have fun reading the table. This is just a fact I'll pull out of the blue. And I'm going to use that in the proof that commitments respect the NAND gate. So we have 3 commitments, C0, C1, C2, and they contain bits. We have already proved that they contain 0 1s, right? So they contain bits B0, B1, B2, and we want to prove that B2 is a NAND of B0 and B1. Okay, and we have this observation that we're going to use. And what we're going to do is we're going to compute commitment NOR C1, C2 squared times G2 minus 2. Okay? And by the additive homomorphic property of commitment scheme, that's actually the same as a commitment to B0 plus B1 plus 2B2 minus 2, which is exactly what we have up here. Okay? Now what the proof will do is it will give a proof that this thing here is a commitment to 0 or 1. And if it's a commitment to 0 or 1, it knows that, well, indeed, C2 contains the NAND of what is inside C0 and C1. So we can reduce the question of 3 commitments respecting a NAND gate to the previous proof we had that a commitment contains 0 or 1. Okay, and again, the proof is of course very simple, right? Because it just consists of one group element that proves this thing here contains 0 or 1. Okay, so that's the construction. Okay, this is the non-interactive zero-knowledge proof, right? We commit to the wire values, make a trivial commitment to 1, so the verifier can check that. We give these one group element proofs that the wires are 0 or 1s. And again, we give these one group element proofs that the NAND gates are respected. And the complexity we end up with is, well, we have a common reference string, which basically is a key for this BGN commitment scheme. So we'll have to specify the modulus n, the rest can be deduced from that, and then it has to specify g and h. So we're talking about something like 2 group elements and a modulus, something like 3k, if k is the length of the modulus. So that's a very short common reference string. And the proof size, well, for every wire we have to make one commitment, that's one group element. we have to give a proof that it contains 0, 1, that's one more group element. So we make 2 group elements for each wire. And then we have to give a proof for each NAND gate that it's being respected. So we have to have 1 group element per gate. Okay? So that's the complexity of a non-interactive zero-knowledge proof. Okay, so what remains is I kind of argued along the way how this is perfectly complete, how it's perfectly sound. What remains is to argue that it's also zero knowledge. So we'll sketch that. So we're going to use this subgroup decision assumption that it's hard to distinguish whether H has order Q or it has order N. So when we simulate the common reference string, we're going to choose H which has order N. And that means we can actually set it up such that G is H raised to tau, and tau is the trapdoor, okay, associated with the common reference string. And now the commitments, they're no longer perfectly binding and we don't get perfect soundness. Actually, the commitments are now perfectly hiding. And in particular, you can have a commitment to 1 and at the same time interpret it as a commitment to 0. Right? And indeed, if you know the trapdoor tau, then you can give a commitment that you can open both as 1 or as 0 as you please. So in the simulation, simulator will do the following. It will just commit to all 1s because it doesn't know what the witness is. And then it will simulate proofs that these wires are 0s or 1s. That's of course very trivial because they're all 1s, so it can give these kind of proofs. It will just run the regular proof algorithm for that. And then it will simulate proofs that the wires respect the NAND gates, and it can do that because it can make, for each NAND gate, it can make a trapdoor opening of the output, right? So we have here input 1, and this commitment here to 1, when you have the trapdoor, it can also be interpreted as a commitment to 0. And then indeed the NAND gate is respected and you can give the proof. Okay, so we still need to argue that this simulation works out, that it's indistinguishable from a real proof. And I'm going to use as a tool here that these 0-1 proofs, that a commitment contains 0 or 1, they're actually witness indistinguishable. Okay? And witness indistinguishability makes sense when H has order N, as it has in the simulation, because now commitments could be 0, they could be 1 at the same time. They're witnesses for both. What I'm going to argue is that these proofs, they don't reveal which of those witnesses that you have used in making the proof. Okay? So we can write the commitment as G to the W, H to the S, where W can be of either of the forms either 0 or 1. Okay? And doing some computations, we see that we can reveal this proof. And what the verifier will check is that this relation here holds. And actually at this stage, I can argue directly that it's witness indistinguishable. And the reason is that H has order N in the simulation, okay, which means that there's one unique possible proof that will satisfy this equation. So in other words, we do have perfect completeness, just as before, but no matter whether we started out with one witness or the other, we will end up with in the same proof, right? Because there's only one possible proof that can work. So in other words, whether we use one witness or the other, we end up with exactly the same proof. In other words, the proof is witness indistinguishable. It doesn't contain any information whatsoever about which witness it was that we used, whether W is 0 or whether W is 1. So now let me return to the zero knowledge proof and give a sketch why we have zero knowledge. So let's start with the probability. What is the probability in a real proof where we have a real common reference string where H has order Q? We give a real proof. Okay, and what is the probability that adversary guesses 1 in this case? Okay. Well, it's going to be about the same. It's going to be indistinguishable from the case where H has order n. That's by the subgroup decision assumption, right? Can't distinguish whether H has order Q or H has order n. Okay. So now we have a kind of a hybrid in between those, between the experiments now where we generate H with order n and then we run the real prover with the witness. And now let's modify the experiment a little more. So we actually make commitments to 1 all the way when we generate proof, and then we do trapdoor opening to whatever the witness is. And by the perfect hiding property of the commitment scheme, those two experiments are completely indistinguishable. So the adversary has the same chance of outputting 1.